Well, I'd like to welcome you all to this seminar to be given this afternoon by Dr. Michael Manley from the Oak Ridge National Laboratory, the Materials Science and Technology Division. My name is Erland Schulzen, and I will be chairing this seminar today. And firstly, I want to welcome Mike back to Dartmouth. You'll understand why I'm saying that very shortly. Academically, about Mike. Mike has a Bachelor of Science in Mechanical Engineering, 1992, University of Massachusetts. He has a Master of Science in Engineering in Material Science from Dartmouth Thayer School, 1996. That's why I'm saying welcome back. And again in Material Science, Mike has a PhD from Caltech in 2001. Having completed his PhD, he took up his professional life, initially first at Los Alamos National Laboratories from 2001 through 2006. So I have that right, about 5 years. Following Los Alamos, he moved on to another national laboratory, Lawrence Livermore Labs, from 2006 to 2012. I think that's right, about 7 years there. And then since 2012, he's been at Oak Ridge National Laboratories in Tennessee. 8 going on, question mark, number of years at Oak Ridge. Mike there is a senior scientist, and one of his responsibilities in terms of doing a lot of research, which you're going to hear some of which you're going to hear, he is the co-director of a new program, I think it's a new program, their school, a national school of neutron and X-ray scattering. Co-director is he of that program. Mike has made many contributions to the scientific literature, roughly about 80 papers these days. Largely, if I just say, correct me if I'm wrong, but sort of in lattice dynamics, things moving around within the, you're going to hear about this in detail. So things moving around within the solid state, atom dynamics. You're going to hear about this, lattice dynamics. Many of this work has been published in some pretty prestigious journals. If you look, Nature, many of them, PhysRev Letters, Science, etc. Materials World, More Film, Philosophical Magazine, Active Material. So Mike's been very productive, very productive. And in recognition of his productivity and contribution to the field, a number of awards, and the most recent that we notice here was given by the Functional Materials Division of the Materials, Metals, and Minerals Society, TMS. It's a fairly distinguished award, the Distinguished Scientist Award. So Mike, we congratulate you on being recognized by the TMS FMD division. Now, today, Mike is going to address the topic you see here, energy materials, advances made while watching atoms move. And so without further comment, Dr. Michael Manley, please take it away.
Thank you. Yeah, it's great to reconnect with Dartmouth after all these years. Yeah, I'm going to talk about energy materials. We'll talk about a couple of examples. So advances in energy technologies depends very strongly on material science and advances in materials. And I work on a few different areas. I'm part of a large group that looks at thermal transport under radiation in nuclear fuels. Nuclear reactors, the starting point is removing heat from nuclear fuels. And one of the issues is that over time, because they are radioactive, they accumulate defects, and that suppresses the thermal conductivity. So there's a large effort on that, a 7-institution effort that I'm part of. The second area, which is actually new to me, that I'm going to talk about today, are some recent work on solar cells, in particular trying to improve efficiency by looking to 3rd-generation type solar cells, where we try to keep carriers hot longer so you can basically extract energy from the solar cell more efficiently. And the last example that I'll talk about is with thermoelectrics, which convert temperature gradients into electricity. And in that case, you need to control the flow of energy through the vibrations in the material, because that controls the transport. And you need basically to support a temperature gradient in order to have a thermoelectric effect. So okay, so what do I mean by atoms move? This is the problem of lattice dynamics. Um, so when we look at atoms moving, we're doing a scattering experiment, and that necessarily lends itself to putting everything into reciprocal space. So it's the same as doing X-ray diffraction, except we also include energy. And so in diffraction, you'll know you would have a scattering angle or a momentum, which depends inversely on the wavelength. And at the same time, we have an energy variable, which is, or frequency, which is the inverse of time. And we measure something called a phonon dispersion curve, this is a simple example of a phonon dispersion curve. And you have to recognize that things are inverted. So down at the bottom, we're talking about long wavelengths, and right at the bottom here, we're talking about sound waves, basically, in the material. And then as you go up the curve, you're reducing the amount of material between the peaks and troughs as you make these wavelengths shorter and shorter. And so the frequency goes up and up until it can't do that anymore because you run into atoms, and you can't make the wavelength any shorter, and you essentially get a standing wave. There's another thing that you have to appreciate here are a couple of things. The slope of this line is the velocity. So that's basically how quickly energy is moving through the vibrations in the crystal. So that's an important parameter. Another parameter is that if phonons lived forever, if the vibrations lasted forever, this curve would be sharp. But it's not sharp because the vibrations scatter from things, from defects, from other vibrations, and so on. And what happens is that causes this to broaden out. But when we do a measurement, if we can measure that width, that's inversely proportional to lifetime. And that's another factor that comes in. So at the bottom here is the thermal conductivity using a gas model. And you'll see that the velocity comes in squared, and then there's a lifetime. And the specific heat is also related to the dispersion curve. So we can get that as well. So that's one type of vibration we study. We also look at, I will give an example where we look at molecular modes, and they can have another variety. So of course they can have vibrations, but they can also have rotations, and then a thing called the libration, which is kind of a rocking of the molecule. And I will bring those up in more detail. But what's really interesting from my point of view is when you can get these things to interact by embedding a molecule into a crystal, and then you can start to tune the vibrations and can change properties. The third example that I will talk about in the second half of the talk is basically, I'll start talking about nonlinear modes. So this is kind of the more advanced part of the talk. And I will talk specifically about intrinsic localized modes. So you have your phonons here. These are your normal phonons, but in addition to the phonons, you get this extra patch of intensity that pops up here, which represents an intrinsic localized mode, which is interesting if you're looking at thermal conductivity because it is a mode that isn't propagating. So you basically locked energy in, and it occurs in a perfect crystal, which turned out to be very interesting from the point of view of a thermoelectric, where you want to stop the heat from flowing, but allow the charge to flow. And so I'll talk more about that in the second half. Okay, so the first part is looking at a giant isotopic shift in the phonons that keeps charge carriers hot longer in a photovoltaic perovskite. This is an exciting new class of materials, and what I'm going to do is show you how we can adjust the materials in such a way as to improve their properties for certain types of photovoltaic applications. Okay, so these perovskites kind of burst onto the field in around 2009, and I say they burst onto the field. If you look at how the efficiency of photovoltaics increased with time, this is basically going from 2009 to 2013. They jumped from around 3%, 3 or 4% up to 16% in just a short period of time, and now they're already over 25%. And so they're very exciting. The kind of general attraction of them is that they have a sort of flexibility that you would get with organic materials, but they're a little bit more stable. So like a plastic or something. This is organic photovoltaics. They increase quickly, but they tend to get damaged by the sun and so on. So the whole, one of the attractive features is that you can do a lot with this molecule to change useful parameters, say the band gap or what have you, which is important in solar conversion efficiency. The other factor is what I'm going to focus on, is that they tend to have long hot carrier lifetimes. What this means is that when you create the electron hole pairs, or when photons come from the sun and they create electron hole pairs, the charge carriers, they live longer than in most materials. And, um, and that is because of what we call a phonon bottleneck, which is, or a hot phonon bottleneck. And this is just a recent review article talking about this, that the electrons are unable to transfer their heat efficiently to the lattice vibration. So they transfer quickly to the optic phonon, but then there's this path where they have to exchange energy with an acoustic phonon, and then that has to spread out and decay. And so this is sort of, when I look at this, this is my in, because I study vibrations and phonon dispersion curves. So I'm going to look at how to do that. But before I do that, I want to just say, for people who aren't experts on solar, so the material challenge is to further increase this hot carrier cooling time. But the real question, and I guess at this point, is why? Why do we want to do that? And so I want to explain that to you very quickly. So to understand that, you have to go back a bit to kind of probably the most famous paper in solar energy, which is this Shockley-Kacer paper from 1960, where they went and they took the spectrum of the sun, and then they started to consider, okay, what efficiency can we get? And they have a plot here, and this is the band gap. So essentially, if you make your band gap too wide, then you're basically letting photons of energy below the band gap pass through, and so you start to lose on that. If you make it too narrow, you start to get into this relaxation problem, which is, and this detailed balance, they call it, which is to say that you're creating electron hole pairs, but some of them are recombining and giving off photons, and you can do different things to catch them. But basically, in a single junction, first generation solar cell, the maximum you could get based on this was about 33% efficiency at a band gap of about 1.3. So there was some optimum there. And since then, people have been able to go beyond this, and they do it through complex architectures where you put a series of absorbers to collect more. But there is another way that people are looking at, and this gets to the hot carrier problem. So you can make a more efficient solar cell if you can extract your charge carriers before they have a chance to lose their energy to heat. And what happens if you do that, you get this, a different power output, and you will essentially double your efficiency. And some of you may recognize this extra term here. This is that's a Carnot efficiency, because essentially what you have, you have a sort of internal heat engine, and then you've basically recovered a lot of that. But you can't recover all of it, of course, because you still have to pay Carnot. But the idea is, if you can pull the heat off, if you can pull them out higher, you're going to get a much higher Carnot efficiency. And this plot here on the right shows that as a function of hot carrier temperature. So as you push the hot carrier temperature up and up, you get more and more efficient conversion. And so, but the sort of the challenge is to get those heat carriers out before they cool. And there's different aspects of the problem, but one of the problems in the materials science problem is to increase the carrier lifetime. Okay, so I'm going to talk a little bit about that, but we're going to try to increase the carrier lifetime in a sort of a nice controlled way. And so in particular, we're going to look at the problem when you substitute an isotope. And the reason we do that isn't because we want to make, put isotopes in real material so much as it allows us to change the vibrations without changing the electronics. And so I will talk about how we will look at compare two cases, one with the hydrogen replaced with deuterium. So we double the mass of that on the molecule. That'll change the dynamics, and we'll talk about that. So first of all, this is a classic, the initial measurement that I'm doing here is a classic triple axis, what they call triple axis measurement of the phonon dispersion curve. You start with a neutron source. That allows you to select any incident wave vector you want in the range that is possible out of the reactor and the moderator. But you can pick an incident wave vector that scatters off of your crystal, to scatter in every direction. But what you do is you have this analyzer crystal on the other end, and that allows you to select a final wave vector. And between the two of them, you can scan energy at a fixed position in reciprocal space. The key point about neutrons to recognize here is the reason that this works so easily with neutrons is because neutrons simultaneously have wavelengths of order the spacing of atoms when they have energies on the order of the energy of vibrations, a few millivolts. Okay, so on the right here, I'm giving you a summary of the dispersion curves. So there's a couple of things here. So first thing is that there's two different colors here. There's the black. The black is the deuterated, and the purple is the protonated. Now, the first thing that happens is that, and we did an additional measurement down here for the high energies on the time of flight instrument. I'm not going to go into the detail, but what happens is in the molecular dynamics, the molecular libration mode is slowed down when you swap out hydrogen for deuterium. That's not surprising, because this is basically the mode rocking back and forth. Now you're doubling the mass of all the hydrogen on the end. So now it's going to rock a little bit slower. That's the libration mode, okay? So that part slows down. But the interesting part, and the part that was a little bit surprising to us, was how strongly affected the longitudinal acoustic phonons were. So this is the longitudinal acoustic phonon. You notice it has a very steep dispersion. It's a compressional wave in the lattice, and it gets pushed down. So it's what we call this mode repulsion. So the longitudinal acoustic phonon is slowed or repelled by the pushing of this libration mode down. That means that this libration is coupled to this phonon, and you see it in the other direction. So we call this gamma to X. That means it's propagating through the face of the crystal, and this one, gamma to M, M is on the edge of the crystal, so it's kind of propagating along the edge. And you see an effect there as well, though it's stronger along this direction. So I know I don't expect you to be familiar with this, so I'm going to try to explain to you why mode repulsion happens in general. It's a really general effect. It's the same thing that happens in chemistry when you have bonding and anti-bonding and all that. So I want to just take this time to explain why this happens. So if you have two springs, one that is stiff with the same mass and another which is soft, so you have one that's oscillating very slowly and the other one's oscillating faster. Imagine that you change the mass or you change the spring constant over time so that one crosses the other. Now, if they're uncoupled, it's not a problem. You can just go right through one through the other. But what happens if you couple the two? If you couple the two, then when you try to go through this point, when you try to get them to be the same, or degenerate, as we would say, it doesn't work. And what happens is the mode will split. So as long as the frequencies are far apart, they'll sort of act like independent oscillators. But once they get close, they'll split into two types of modes. One which we call the antisymmetric mode, and one which is the symmetric. So the antisymmetric mode is basically one of the two vibrational modes. These are the normal modes of the system. If you write down equations, you end up with a coupling term between them, and then you end up with another. Basically, you still have only two modes, but they're mixed, and one will be, so they're hybridized, if you like. One they'll move out of phase, and the other they'll move in phase. So whenever you see in spectroscopy, you see two vibrations or phonons. In this case, it's a localized thing, the thing that's oscillating, that's coming in contact with it in terms of frequency space. That means that they're going to basically start to hybridize. And the one that gets pushed down is the one where they're moving in phase, and the one that gets pushed up is this because it's engaged in the coupling. It's kind of a general concept, but it applies all over the place in spectroscopy. Okay, so if you don't understand that in detail, the main picture to think about is that you have this vibration that is propagating, say, in this image here, and it's a compressional wave. So it's squeezing, expanding, squeezing, expanding. And as that happens, if the molecular mode, this libration, has a frequency that gets close to it, then it's going to start to drag it along. And that lower mode is going to basically be dragging this thing along, and it's going to slow down the phonon. And so that's basically what's happening. So the molecular libration slows down because I've made the N groups heavy, the hydrogen heavy, by swapping it with deuterium. And then this lower vibrational frequency in turn slows down the longitudinal acoustic phonon. So that's very interesting. And it opens the question, if you go back to this equation for thermal conductivity, the thermal conductivity depends upon the velocity squared, and this is a large contributor to the thermal conductivity. We weren't really sure which way this was going to go, but we had a hunch that it would go down. And in the next part of the talk, I'll talk about how you can get tricked by these things, because you get one effect in some places and things happen in other places. But it turns out in this case, this did just what we wanted it to do. And we did that. We did additional measurements of the thermal transport. So this is comparing the protonated and deuterated sample. This is what we call the thermal diffusivity, which is looking at the diffusion of temperature in the materials. And you see the thermal diffusivity in the deuterated case is significantly lower than in the protonated case. It's down by about a factor of 2. Now, to convert this into thermal conductivity, what you need to know is how much heat capacity that is being carried. So we measured this, but it doesn't change too much because that's basically just determined by the population of all the modes, and the modes are going to be all populated at these low energies anyways. So it doesn't really change the outcome, but the bottom line is that the thermal conductivity was decreased by about 50%. So this is exciting because this is what we want to see, because remember, we want to basically insulate the electrons or the charge carriers and holes, the electrons and hole charge carriers from losing heat. And when you reduce the thermal conductivity, that helps. And I also want to point out this thermal conductivity is really low. So 0.5 watts per meter Kelvin is already really low. We're down at 0.29. That's basically like, like a plastic or something. Okay, so knowing what we knew, we had to, in order to see, the next step was to look at the charge carriers. Now, the first thing we did was we talked to, I contacted my old friend Mark Asta at Berkeley and said, well, we have this problem. We want to know, is this effect going to survive when the thing is in operation? So once you put hot charge carriers into the system, you could change things. And so we knew from other measurements that, for example, when you irradiate the material, you're going to have hot electrons. It basically expands the volume a little bit, about 1.4%. So he did that in a calculation and looked at that phonon, looked at the 2 phonons that we were studying, and both of them basically didn't do anything. He also introduced a distortion and finally made the electrons hot. And that basically softened them a little bit, so it didn't reverse the effects we were looking at. So that gave us the confidence to, okay, go to the next level. And we talked to a young staff member, Cheng Yunghua at Oak Ridge, and who did a lot of work on transient absorption. She had to basically build a whole system to do this, but she did. And she did some optical transient absorption measurements where you basically pump the system, release charge carriers, and then you look at reflections from it, and it basically bleaches the system, and you look at how that decays over time. So this basically, the main point here is if you look at it as a function of time, in the protonated case, you get a decay time of about 500 picoseconds, which is actually really good to begin with. But in the deuterated case, where we have this suppressed thermal conductivity, the lifetime increased to almost about a nanosecond, 1,000 picoseconds. So the deuteration doubles the hot carrier time by enhancing the phonon bottleneck effect on the charge carrier. So that was exciting. So I'll just say, what is 1 nanosecond? For context, this was a paper written a few years ago, but in 2009, where they had said, okay, this is kind of a critical look at hot carrier solar cells. And they said, we'll let the achievable, optimum possible condition for the thermalization time be 1 nanosecond. So we're at 1 nanosecond, so that's pretty nice. And with that, they said, well, maybe we can get 50 to 55% efficiency. But I don't want to say that we're going to, like I said before, the whole point of this is to understand how to control the thermal transport, not necessarily to make material specifically this way. Because now we can look at, say, you change the molecule in such a way, chemically, you could maybe make a change that moves the band gap the way you want, or something else. And you also want to look at, oh, maybe we can gain something on the carrier lifetime. So that's the idea. And it really is, it bears new strategies for achieving conversion efficiency. Okay, so that's the main point of the first part. I just want to say a little bit about some future stuff that we can do on here. So there's another possibility with these materials. People are looking at them as potential thermoelectrics. And the figure of merit for a thermoelectric looks something like this, which is, it has this thermal power in the top. This is the electrical conductivity, Seebeck coefficient. And in the denominator, there is the thermal conductivity. And so if you can suppress the thermal conductivity, you can improve the efficiency. This is a recent paper where they looked at possibly using this material, actually methylammonium lead iodide, for a thermoelectric. And they optimally doped it. It's a theory paper, so you can take what you want. But in order to reduce the thermal conductivity, they looked at thinner and thinner layers, and they could push it up to some level. But but now we have this knob, like we can, decrease the thermal conductivity. Maybe we can get this higher. And then we can also, if we can, decrease the thermal conductivity, At 1.5 is a pretty high number. I think the record right now is about 2.6. I don't think anything's gotten over 3, but you get above 3, you start to get into ranges where things become practical. So that's a potential future direction. Okay, so now I want to talk about another problem, which is I'm going to get into some nonlinear physics here, which I think is really fun, and particularly the nonlinear stopping of phonons in a thermoelectric crystal. So I think it's interesting. Nonlinear science is kind of this whole field, but I liked Stan Ulam from Los Alamos had this quote saying nonlinear science is like calling the bulk of zoology the study of non-elephants, because I mean, linear problems are all over the place, but there's so much more variety of nonlinear effects. You see that if you go to the beach and you look at the ripples of waves, those are not sinusoidal waves. Those are sinusoidal waves. They interact with each other, and they do all kinds of interesting things. Dramatic effects, tornadoes on a larger scale, or large coherent structures in the ocean, or even planetary scale things like on Jupiter. And so I've always been interested in this idea that, well, sure, the vibrations of atoms and crystals are also highly nonlinear, so they should exhibit interesting effects. And I've done a lot of work on that. And we're always finding new things. This was a paper that's just been accepted, where we see nonlinear propagating modes in the dispersion that occur 40 to 60% higher than the maximum phonon frequency. And this is in fluorite. This is fluorite, but we've seen them in every fluorite that we've looked at. They're always there. And so they're not phonons, they're nonlinear modes. I've looked at phasons, which are basically vibrations in a soliton lattice, and they're motions of atoms, but they're not translations, they're reconfigurations. In this case, they move 3 or 4 times faster than the speed of sound. So you can get some really counterintuitive things when you go nonlinear. And they do that because they distort the properties as they propagate through, kind of like warp drive. If you're a Star Trek fan, they warp space-time. It warps the material. And then finally, the one I'm going to talk about today, which is the first one that I discovered in materials by accident in the early 2000s, is the intrinsic localized mode, which is interesting because it basically results in vibrations that stop moving in a crystal because of an interaction between nonlinearity and the discreteness in the lattice. And I say this is a kind of a nice thing for a thermoelectric, because thermoelectrics, the goal is to basically stop the transport of phonons, but not disrupt the transport of electrons. And that can be tricky, because if you try to put in defects to stop phonons, or grain boundaries and other things, you also run into this problem of affecting your electrons. And so this is kind of a nice thing to look at in that sense. So that was one of the reasons we were interested in this. Although I got into this by complete accident, which I will explain in a moment. First, I want to explain where this came from. So, what's the kind of conceptual idea behind it. So you have to understand, you have to go back to asking the basic question as to why do waves propagate in the first place? So if I throw a rock into a pond and you see the ripples spread out from the center, why does that happen? Well, in a simple way to think about it, the reason that happens is that you've created a disturbance in the water that goes up and down at the same frequency that everything around it does. And so it's in resonance with it. So the energy just spreads out. That's kind of the immediate spread. And that's the same thing with a crystal. If you vibrate a single atom in a crystal, it'll resonate with everything around it. And so it'll propagate waves outward. But that is not necessarily true when you introduce nonlinearity. And the reason is with nonlinearity, the frequency of the vibration, or the elastic properties locally, can be augmented by the vibration itself. And so if you have a soft nonlinearity, it can create a lower frequency locally. If it's a hard nonlinearity, a higher one. So you could have some jiggling atoms that are occurring at a higher frequency than you expect. Okay. And it occurs in really simple systems. So my colleague from Cornell, Al Sievers, used to carry around a suitcase full of pendulums when he'd go give a talk. And he had this motor that would start shaking the pendulums. Now, pendulums are intrinsically nonlinear because it's because of the swing. It's only linear on a small amplitude. And if you let them swing for a while, so he would give his talk and you'd watch them swing, eventually all the energy will end up in just one pendulum. So this is like a really sort of basic idea. And it's amazing to me that it wasn't actually discovered until the 80s, but by Al Sievers. He discovered it theoretically, and then I kind of stumbled upon it experimentally. But yeah, this is a simulation, but this is what happens over time. The energy will just end up concentrated in one. Okay. So I had first observed them in uranium, but then I got in contact with Al Sievers because he had done some calculations. I said, let's look at this example. So the first one we looked at was after the uranium, which is where I first saw it. We looked in sodium iodide, and he had these simulations which weren't like the kind of simulations that we do now, but it was, you started with the frozen lattice and you tried to find an orientation. They do this thing called a simulated anneal, where they would create the vibration in some direction and then maybe distort the lattice until you got something that was stable. And they got a vibration that was stable, a localized vibration that was stable, polarized along the 111 direction, and it came with a distortion, a slight distortion of the lattice around it. And they made a prediction that it would appear there, and we went and we measured it, and the first time we found it, but it occurs at high temperature, so it doesn't exist at low temperatures. And as you go up in high temperature, this thing appeared in the gap. But you know, so ever since we did that, I've always been interested in finding some place where this kind of strange behavior is useful. I want to say something about nuclear energy, because I looked at this in uranium first, and it seemed like an interesting retrospective. If you look at it, so as I mentioned, it tends to contract the lattice in the direction that it's polarized in. This localized mode in uranium appears around 450 K or 200 C. And if you look at the thermal expansion in uranium, at that temperature, it undergoes a big change. So the the positive thermal expansion along the zero, the B axis in the crystal, 0, 1, 0, goes from positive to negative, and the other two directions go more positive, which is what you'd expect if you introduce ILMs. But what this has in effect, if you think about mechanical properties, is that what happens is if you put this in a polycrystal, one grain could be adjacent to another grain, where in one of the grains it wants to contract, and the other grain it wants to expand. Okay, and when you change temperature, but they're attached, so they become stressed, and stress builds up. And there's this quite an amazing picture here. This is a piece of thermally cycled growth of a highly oriented uranium grain. It grows from 2 inches to 11.5 inches after 300 cycles from 50 to 550 C. So this stuff just basically tears itself apart. And you can see this. So anytime you thermally cycle uranium through these, over a wide temperature range, it will kind of tweak itself a little bit. I mean, this is a dramatic example, but it will always tweak itself a little bit because the internal strains are large enough to go plastic. And so they don't completely recover. And so it kind of builds up over time. And as Jerry Lander wrote in in a review article in 1994, this surely represents one of the most rapid changes in technology driven by basic research. And the reason is because when they saw this, and then there was also an effect of radiation swelling, they said uranium's out, and that kind of ended the application of uranium metal in reactors. So they had to switch to oxides. So, but there are ILMs in there, so I find that interesting. But this is just an association, and it's in hindsight. So I needed advances. So something happened a few years ago at Caltech. There was a Austin Minich's group in the mechanical engineering department there. They were improving their simulations of phonons, and a lot of this has to do with Ole Hellman, who developed this technique called these temperature-dependent effective potentials. But essentially, the ideal thing you want to do with a first principle calculation when it comes to phonons is do what they call ab initio. You want to basically recalculate the electronic structure at every instant in a molecular dynamics simulation. That's the way to be exact, right? So none of this, classic approach where you kind of just freeze in distortion and get force constant. And so they have, but that's very expensive computationally. But Ole came up with a way to do this where you kind of let it go, calculate it instantaneously, and then accumulate information that allows you to extract force constants, first, second, third order, and higher order, and then do a simulation that includes everything. And then you just calculate the spectral function. And they did this, on lead selenide, and then they looked at it at high temperatures, and you notice they got this localized thing here, this flat band. So I say it's localized because it's not propagating. It has 0 group velocity. And the velocity, of course, is the slope. And they were looking at this and saying, what is this? And then they, affected the thermal conductivity. And as the story really goes, that they were in a mailroom staring at this, And then my old advisor at Caltech walked in and they said, what? And he asked them, what is this? And he said, oh, you should talk to Mike. And that's how I got connected with this project. So this is very exciting to me because it's just coming out. They didn't try to make it. It just appears in the simulation. And since then, they've been seen in lots of simulations. You just had to get the simulations to basically work in this way, where they're very exact and include all of the anharmonic effects. So we got together and we started doing experiments, and we can see that, not everything is exactly as predicted, but there were certainly things that came together. For one thing, as we heated it up, if we look at this transverse optic phonon, so this is the transverse acoustic, longitudinal acoustic. There's one thing that's really interesting is that this mode goes completely flat, means that it's no longer propagating. It's the entire phonon, and it also splits up. Another thing that happens, which wasn't expected, and I will explain this in a moment, but the longitudinal acoustic phonon, when that branch went flat, longitudinal acoustic phonon became sharper, which is kind of frustrating because a sharper phonon means a longer lifetime, which means it's going to increase the thermal conductivity. So we had this thing decrease in one place and increase in another place. So there's kind of a whack-a-mole thing, but I will explain why that happens in a moment. There's actually a lot to explain here. So let me go through some of this. The first thing is we went and we did a higher resolution measurement with a cold neutron source. And we were able to pick up some more detail, like as this thing starts to localize, it does actually splinter off a piece like this, although it's not as dramatic. The other problem, there is a problem here with the calculation in general, in that, for example, just the normal phonon, the transverse acoustic phonon, is much too high. And I think that's preventing this whole branch from appearing flat completely. There was a shift in intensity. If you go to higher temperatures, you start to kind of recover that. So there's still some work to be done. But I will say that this calculation is done without any, you don't do anything to control anything. It's first principles based. You just let it go and you see what you get. And so the fact that it could tell us where to look and find localization was great. So I want to explain something that it actually does pick up, but it's tricky to understand why it happens. But why does the whole branch go flat when you get this localization? I'd actually seen this before, so I had a kind of an explanation in the back of my head. If you take a simple model, like this is the problem for phonons in Kittel, which is you have a lattice of atoms, one-dimensional, and if you make two atoms, you get an optic phonon. So the optic phonon is like your asymmetric mode. Everything will move out of phase. The acoustic phonon is like your symmetric mode. Everything moves in phase. You get this optic mode. But if you want to artificially create a local mode, you can just soften the lattice around it. So that's effectively this, like making the ILM, but kind of cheating, and do it linearly. And when you do that, and then you calculate everything, you basically made a supercell, so you have to unfold it. But what you'll find is that you get a very flat optic band, and you get this local mode breaking off. And the reason that happens is when localization begets localization. So once you start putting these soft spots in there, it actually starts to trap other phonons. So at each of these boundaries, you get phonons that are once they become multiples of this distance, they become standing waves at that distance. And so this tends to flatten the whole thing. So that's partly why that happens. The other thing, though, is that this change occurs fairly abruptly, which is something we'd seen before. In sodium iodide, there are transitions where they'll order into different states. So you get the local modes will form patterns. And so we wanted to see, is there anything happening there? And we know that we could pick them up. It tends to be subtle. It's not like a structural change. And we keep track of the structure at the same time, by the way. Our data sets are huge. They're 4-dimensional data sets. They have all the diffraction data. They got elastic diffuse scattering, inelastic scattering, everything. It's all contained. And this is a small section of it because this is a cold neutrons. But we can measure the same phonon maybe 100 times in a single measurement, over and over again. And we measure the structure at the same time. But this is a thermal diffusivity measurement, and again we can see that at the temperature where we see this kind of jump in the lattice dynamics, we do see a kink here. It's a very subtle effect, but we see the thermal conductivity going down and then recovering back up. And remember, the LA phonon was becoming sharper. Now, I want to talk a little bit about that. So we repeated this measurement because we were kind of surprised. Phonons are not supposed to become sharper with increasing temperature, because as you increase the temperature, there are more other phonons for it to scatter from. But sure enough, we repeated it with X-rays, and we got the same result. It didn't matter. The numbers were the same. The lifetime of the phonon was basically half at 700K or 770K as it was at room temperature, which is really surprising. So, and this is of course cramping our style because we're getting localization stopping one phonon, but at the same time we're getting another phonon which is able to propagate more easily. So it's sort of, you know, compensating, and so we have this sort of problem. So why did this happen? And this is a kind of a real, I think this is a more realistic example than the last one, because this often happens in material science where you try to change one thing and something else you don't expect changes. So let me try to explain. This is the last thing I'm going to try to explain, and it's the hardest thing. And but the concept isn't that hard, but it's just complicated. So basically, in order to scatter, for phonons to scatter off of each other or to transport heat, it's dominated by 3 phonons scattering. So you have 1 phonon maybe creates 2 phonons, or 2 phonons come together and create a third one. But in order for that to happen, you have to satisfy conservation of energy and momentum, just like anything else, right? Now, all the combinations of energy and momentum is kind of complicated. But in this case, I asked Ole to do these calculations for me. So he calculated these all the combinations of the transverse optic phonon that's moving most, the one at the zone center, and all the scattering conditions for that mode and the LA phonon. So you create 3 phonons, any TO phonon, any LA phonon in any direction with the 1 TO phonon at the center. And then that TO phonon is now moving. And this is captured by the simulations. And then so what he does is he calculates what is the phase space for that scattering process. And this picture that he made represents everywhere in the zone where the 3 phonon scattering processes are occurring. And what happens is as you raise the temperature, this phase space basically disappears. So this is a basic problem with the assumption that we often make, which is, oh, phonons become broader at higher temperatures because you populated more of them. But we just assume that the phase space for scattering isn't changing. But what happens when you have a phonon move a lot, you can change the scattering conditions in ways that are very hard to predict because you have a big complicated space of phonons and 3 phonon scattering. What happened is that the phonon basically, the localization of one phonon freed up another phonon to travel more easily because it moved something out of the way that it was scattering off, okay? Now, so future directions on this particular problem is to look, can we block that LA phonon? And it looks like maybe somebody's done that. This is from another group that we collaborate with, looking at lead selenide with dislocations added. When you add dislocations, the thermal conductivity does go down. It doesn't recover up at these high temperatures. And one possibility is that we know that the dislocations tend to scatter longitudinal acoustic phonons easily. So it could be that in this case, localization is happening and we block the LA phonon, and maybe that works. And so this is from Jeff Schneider's group at Northwestern. So we have to look though. We don't know. We can look, we can check this experimentally, and then potentially get the ZT up. Okay, so this is, I'm a little bit over, but the conclusions here are basically that advancing energy materials in the future, but in this case, I'm talking about renewables, will require advances in materials, and those advances will require some, a fairly detailed look at what are the underlying mechanisms controlling things like the transport of energy away from the charge carriers in the solar cell, or the ability of a material to support a thermal gradient in the case of a thermoelectric. And I think these are becoming increasingly important. And I think, our future depends upon it. The science is hard, but it does work. And I think I'm ready to answer any questions anybody may have on this.